Hi, everyone. Okay, so probability exists to describe the likelihood of something happening. And probability exists on a scale between 0 and 1. And everything else is just a decimal or fractional representation between 0 and 1. A lot of probability questions come down to things that you might be familiar with. So, what we have to think about is we have to think about the sample space. And when we think about the sample space, we think about what are all the possible different outcomes for that event. So when I flip a coin, what are the events that could possibly happen when I flip that coin? I either get a heads, a tails. So flip coin, heads or tails. It's either heads or tails. Except for the extremely, extremely, extremely rare chance that it lands on its edge, which is like nearly impossible. So, when I talk about what is the sample space for flipping a coin, I want to know what are all the possible outcomes for flipping a coin. That would be either H for heads, T for tails. And what we do is we talk about that being the sample space. We use the Greek letter epsilon, which is kind of like a squiggly Z. So we would describe the sample space. It's like some sort of like weird, like little. It's like a Z and a 2 had a really deformed child. And that's how you would represent the sample space. If I was talking about rolling a dice, in particular a 6-sided die, what's the sample space that goes with a 6-sided die? If I roll a 6-sided die, what are the possible outcomes that come with that? Yeah, 1 through 6. So, what we actually do is we talk about probability in terms of the results we care about as a fraction of all of the of all of the events. So when I talk about rolling a dice, and I talk about the probability of rolling a 2, how many 2s are on a normal dice? There's only one. So the probability so the probability of rolling a 2 is equal to the number of 2s divided by divided by the number of possible outcomes. So if there's only 1 2 on the die and there are 6 possible outcomes, the probability of rolling a 2 would be, well, there's 1 2 3 4 5 6. So there are 6 possible numbers. I only care about a 2. So my answer is 1 out of 6. If I was to talk about the probability of rolling an even number, how many even numbers are on my dice? There are 3. So the probability that I roll an even number, so PR, so PR even is equal to the number of evens on a dice. That's 3. Possible number of outcomes, 6. And then you would simplify that fraction down to 1 over 2. Right. Where possible, if you can simplify a fraction, simplify it. Let's talk about something that some people might not be familiar with. Now, one of the things that really bugs some teachers about teaching probability is that a lot of the questions that exist on an exam rely on what's called contextual knowledge. And the reason why that bugs us is because not everybody is familiar with everything. It's like me making a reference to a TV show, or you guys making reference to a Marvel movie that I haven't seen yet, or people talking about Squid Game, and I'm like, wait, what? The problem, the big one that a lot of people gets tripped up by, especially people that weren't born here, etc., is the deck of cards. So let's talk about a deck of cards, because a lot of people need to know this for the type of questions that you're going to get asked between now and the end of year 12, and it would help to know what's in it. Now, a deck of cards is normally 52 plus 2 jokers. For all probability questions, we ignore the 2 jokers. So, deck of cards, 52. Those 52 are divided into 4 what we call suites. You've got your spades, you've got your clubs, you've got your hearts, and you've got your diamonds. All hearts and diamonds are printed in red. Clubs and spades are printed in black. If I divide 52 into 4 even groups, that means that there are 13 cards in each suit. All right, so 13 spades, 13 clubs, 13 hearts, 13 diamonds. And then in each suit is an ace, and then the numbers 2 through 10. And then you've got what are called the face cards. You've got the Jack, the Queen, and on the end you've got the King. So there are 13 cards in each suit, 3 of which are picture cards. 4 suits times 13 makes 52. If I was to ask you to randomly select a card from a shuffled deck, and I asked, what is the probability of getting a king? So here king. How many kings are in a deck? Well, there's 1 for each suit. Therefore, there are 4. And how many cards are in the deck? Well, there's 52. Therefore, the probability of you picking a king out of a deck of cards is 1 in 13. By understanding the probability, it also helps you appreciate magic tricks a little bit more. Because when a magician is involved, probability goes out the window. If they're a good magician, the answer is always 1. One of the important things to remember about probability is that if I look at every possible event in a sample space, if I add up the probability of everything inside a sample space, what will my probability add up to? All right. If I flip a coin, what is the probability I flip a heads? Well, there's 1 head on a coin. There are 2 possible outcomes, so the probability is 0.5. What is the probability that it's not a heads? How many possible outcomes on a coin are not a heads? Well, there's also only 1 at its 2. If I add those 2 probabilities together, I get 1. All right? The probability, all of the probabilities inside a sample space need to add up to 1. All right? And this is useful. This is a useful property because if I can figure out a probability for something happening, I can also use my knowledge of probability to figure out what the probability of the thing not happening. So, I could talk about it in terms of my cards. What is the probability I pick a black card? Well, there are 26 black cards in a deck. 26 out of 52 is 0.5. What is the probability I don't pick a black card? Well, there are 26 cards in there that are not black. 26 out of 52 is also 1/2. The probability I pick a spade, well, there's 13 spades in a deck of 52. The probability I don't pick a spade, well, there's 39 cards that are not spades. So the probability I pick a spade or not a spade still adds up to 1. And that concept, where you're using the probability of something happening to find the probability of something not happening, is called a complementary event. So the thing is that there are a lot of other times where probability isn't known. Say, say I've handed you a like one of those, like a spinner. Like I give you a round disc that's divided into quarters. There's a color in each one. And it's got one of those like spinner arrows on it. And you flick the spinner and it spins around and goes, woo. Well, I wouldn't necessarily know exactly what the probability is of landing on a particular color, because it could always depend on how much force I use to flick the spinner. It could depend on just how precise my color allocations are. It could depend on where it starts. But what we can do is that we can do what are called trials, where I could simply flick the spinner a number of times and I could get a whole bunch of results. So let's let's work together. Can I get everyone in the chat to type a letter, either red, R for red, G for green, B for blue, or P for purple? Pick one of those. Everyone type one of those letters. All right. So every single one of you has now done a trial. So if I go back up in the chat to when this all started, I've got P, G, P, P, G, 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 G. Geez, you guys are a little biased. P, R, 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 P, B. Oh, right. Yeah, that makes sense. All right. So, how many trials did I do? I did 14, I think. Yes, 14. So, there were 14 trials. Excuse me. Rude. So, there are 14 trials. What house color I am? All right. So, if we so we look at our 14 trials, how many purples were there? Well, there were 5. How many greens were there? There were 5 greens. There were 3 reds and a solitary blue. So 1, 3, 5. 14 trials. Based on our experiments, if I flick the spinner one more time, what is the probability that it is going to land on red? Now, some of you might be saying 1 out of 4 because there are only 4 possible outcomes on there. But again, we don't know if this thing is what is called fair. All right? Something is fair if all outcomes are equally likely. Flipping a coin, fair. Only 2 possible outcomes. Each one, if you average it out over the course of every flip that has ever taken place, it comes out to 50-50. Right? The spinner that I've drawn up there looks fair because everything it's in 4 equal parts, but my trials seem to indicate no, something's going on here. Maybe the table is being maybe it's not on a flat surface. Who knows? All I can do is if I know it's not fair, I can still estimate the likelihood of something happening on the next time I roll the spinner. And that is using what is called experimental probability. By using the data from my experiments, from my trials, I can make a prediction about what the next spinner is going to be. All right. And it is very likely that it is going to be a purple or a green result. But to answer my question before, the probability of it being a red, based purely on experimental probability, how many reds did I get? Well, I had 3 on there last time. I have 14 possible trials. Therefore, 3 out of 14 is the answer to what is the probability that the next one is red, based purely on my experimental probability. Sometimes we have to talk about probabilities that rely on other things happening. And this is what is known as a multi-stage experiment. If I flip a coin, what are the 2 possible outcomes? Well, heads or tails. If I flip a second coin, what are my possible outcomes? Well, if I flip a heads first, that means I have either a heads or a tails. If I flip the tails first, well, I'm only going to have a heads or a tails as my second outcome. What is the probability? And this is what is known as a tree diagram. if I talk about the probability of heads, then heads, I can look at my tree diagram. I can look at how many possible branches there are at the end, 4, and then I can look at how many branches actually lead me to the outcome that I want. So H, then H, H, and then H. So how many possible outcomes give me that path? Well, there's only one path that does it, therefore the probability of me flipping a heads, then flipping another heads, is 1 out of 4. Where this gets weird is when I introduce you to the concept of things not being fair. All right. What if I flipped a coin that wasn't 50-50? What if I flipped a coin that was dodgy? How would the probability change if I gave you a coin? Yes. A coin that was 2 out of 3 heads and 1 out of 3 tails. What is the probability now that I flip 2 heads? My tree diagram still works because those are the only possible outcomes. But the tree diagram that I've got up there currently assumes the coin is fair. So what I need to do is I need to go in and I need to take my probability and put them into my tree. So previously, when we did the heads, it was a probability of a half and a probability of a half. And to get a quarter, what do you do with, if you have 2 halves, how do you turn them into a quarter? You multiply them. Well, the same process will happen here. You take the probability of the first event happening, and then you multiply it by the probability of the second event happening. So in this case here, 2/3 times 2/3. What is the probability of that happening? It's going to be 2/3 times 2/3, which is 4/9. And I can go 4/9, and then I look down the rest of them. 2/3 times 1/3. Well, that's going to be 2/9. 1/3 times 2/3 is still 2/9. And then 1/3 times 1/3 is 1/9. If I add up all of these probabilities, are all of my possible outcomes accounted for? Well, 4 plus 2 plus 2 plus 1 is 9, so 9 out of 9 is 1. So even though I've changed the probabilities of the coin, all of the different possible outcomes of flipping that coin still add up to 1. And the same thing will work for any of these sort of tree diagrams, even if it's using different things. If I flip a coin and roll a 6-sided die, what is the probability that I will flip a heads and roll a 1? Right? Tree diagrams are very good for using to map out a possible sample space. So in this case here, heads, tails, or I can roll a 1, a 2, a 3, a 4, a 5, or a 6, or a 1, a 2, a 3, a 4, a 5, and a 6. Tree diagrams can get messy very quickly. But assuming a fair die and a fair coin, what is the probability I flip a heads, then roll a 1? This is a half. This is a half. And every one of these is 1 over 6. So the probability that I get a heads and a 1 is 1 over 2 times 1 over 6, which is 1 over 12. And in this case, all of those outcomes are equally likely. So they're all going to be 1 over 12. But if I change the question, the probability of heads even, well, now we're talking about the heads. We're talking about 1, 2, 3. So what you're going to do is you're going to add up the probability of a heads and a 2, a heads and a 4, and then a heads and a 6. And that's going to be 3 out of 12. All right.